In today's lecture, we will continue from where we left in the last lecture. We will solve some problems on linear differential equations and then some on convertible to linear differential equations, and then we will move on to the new concept called as homogeneous differential equations. Now, in this chapter, the most important techniques are the first two techniques, which are variable separable and the linear differential equation. These two are the most important techniques, and 80% of the time you will get questions only from these two techniques mainly. And homogeneous differential equations technique is actually little lengthy technique. In terms of problem solving, it actually takes a lot of time. So hence generally you don't get questions on this technique. Now when it comes to main standard, mostly you will get questions from variable separable and linear only. But when it comes to advanced, advanced may mix other ideas also. So homogeneous, if it comes, it may come in advanced. And also there is one more technique called as exact differentials. From that also mostly questions may come both in mains and advanced. Okay. So now we will continue with the lecture. We will solve the problems that we left in the last lecture and then we will continue. Okay. So here there is one differential equation. Of course, we want to solve this. Now, if you look at this, it does not contain directly simple variables. There is exponential terms. But also if we try to separate the variables, all terms of x and all terms of y cannot be separated in terms of the product. Remember, all terms of x, all terms of y must be separated in terms of the product to apply that variable separable method. So here it is not possible, even though you could separate x and y from this in terms of product, you cannot separate from the next term. So there must be something here that we may have to do. So what I will do here in this equation is I will try to do this by hit and trial. See, when we see the question, we don't get the idea on the spot. We may have to sometimes do some hits and trials to get the idea. So here I will try to multiply with e power x or e power y or divide and see if I am able to convert this into any standard form or not. Okay. So first I will multiply this with e power y on both sides. So suppose if I multiply with e power y, what do I get? I get e power y into y dash is equal to e power x into e power x minus e power y. Okay. Now here I notice that derivative of e power y with respect to x is e power y into y dash. So here I see that derivative of e power y is written. So now I am getting the idea that if I take e power y as some variable, this will become that variable and this will become its derivative. So that is my idea. So we get ideas only after little hits and trials. Okay. So here my assumption is e power y equal to some new variable, let us say t. So that means dt will be equal to or dt by dx, which is also same as t dash. T dash will be equal to e power y into y dash. So our LHS has got converted into t dash, and now in the RHS we are getting e power x into e power x minus e power x into e power y, which is our t. Now if you notice, it is in the standard form of the linear differential equation. So we write this as t dash plus e raised to x into t is equal to e raised to 2x. Now what is the next step? Integrating factor. So here integrating factor will be e raised to integral of this complete function must come. So in the integral we will get e raised to x into dx. Now what is the integral of e raised to x? It is e raised to x only. So integrating factor is e raised to x. Now what is the next step? Next step is to directly write integrating factor into the dependent variable is equal to, in the RHS, integral of the integrating factor into whatever is the RHS here, which is e power 2x dx. Now, if we just integrate the RHS, we have solved the problem. But now how to integrate this? Because there is a e raised to term and we do not know any standard integrals of that kind. So, we will take this power e raised to x as another new variable, let us say some z. So, here I am going to use this idea of substituting e raised to x equal to z. Then what happens? Z dash will become e raised to x only, or in other words dz is e raised to x into dx. So, what is our RHS here? It is integral of e raised to x into e raised to 2x is coming, but I will write that as e raised to x into e raised to x dx. So, now I will use the substitutions. So, substitutions will give us e raised to z into here I will write z, and in dz also we have these terms. So, we can write this as dz. Now, you know how to integrate this using integration by parts, we are going to do that. So, how to do it? First integrate e raised to z, leave the other function, minus take the integral of the first function and differentiate the z with respect to z, it will be 1 into dz. So, that this is going to give us e raised to z into z minus e raised to z plus c. Okay. So, this is our RHS, but what about LHS? E power x into t. So, this is e power z into t. Now, try to simplify for t. So, for t we are getting t is equal to z minus 1 plus c into e raised to minus z, right. Now, what is t? T is basically e raised to y, and what is z? Z is basically e raised to x. So, put all of them. So, we will get e raised to y is equal to e raised to x minus 1 plus c into e raised to minus e raised to x. Okay. So, this way we can solve this problem. So, here what you understood is sometimes we may have to go for some hit and trial ideas to get the idea. We do not always get the idea just by reading the question. Okay. Come on, make a note of this. This page also. Okay. Now, let us move on to the next question. So, here also if we notice, again it must be in one of the forms, one of the standard forms that we have learned. So, let us first form y dash and see how it is behaving. So, here it looks like x into y dash. Basically, I am dividing with dx to get the dy by dx here. So, x into y dash minus y minus xy cube into 1 plus ln x equal to 0, but I can put equality here by taking one term to the RHS. Now, there is y dash term, there is y term, but there is y cube here. So, now this is in terms of Bernoulli's form. If I can divide this entire equation with this y cube, I can convert this into the linear equation. So, how do I do it? Just divide with y cube. Okay. So, here RHS will be completely a function of x. Now, what are the substitutions that we got to use? We have to use 1 by y square as our new substitution, new variable. Let us take it as z. So, here 1 by y square term comes. So, we are taking that as the z. Then z dash will become minus 2 by y cube into y dash. Okay. So, which means y dash by y cube can be written as minus z by 2. So, here I can write x into, sorry, this is minus z dash. Okay. So x into minus z dash by 2 minus z is equal to x into 1 plus ln x, right? Now to convert this into standard form, we may have to make sure that the coefficient of z dash is always plus 1. So for that we have to divide or multiply, we have to manipulate, okay. So one thing is clear, we have to multiply with minus sign, and other is we have to multiply with 2 divide with x, okay. So it becomes z dash here and it becomes 2 by x into z here, okay. And next again minus 2 by x we have to provide, so it becomes minus 2 by x into 1 plus ln x, okay. So this x is luckily cancelled. Now this is in the standard form. What is our next step? To go for the integrating factor. So what is the integrating factor here? Integrating factor is equal to e raised to integral of 2 by x into dx. You know the integral of 1 by x, which is the ln x. So e raised to 2 into ln x we get, which is also same as e raised to ln of x square, which is also same as x square. So we got the integrating factor as x square. What is our next step? Next step is integrating factor into dependent variable, that is x square into what is the dependent variable here? It is z, is equal to integral of integrating factor into whatever is the RHS. So here RHS is minus 2 into 1 plus ln x dx, okay. See, if you remember these steps, we are just following 2 steps. One is integrating factor, next is integrating factor into dependent variable is equal to integral of integrating factor into RHS, okay. So now we will simplify this. So x square into z is equal to minus 2 is outside, integral of x square into 1 plus ln x dx. How do we integrate this? By using integration by parts. So here there are 2 terms. One is the algebraic function, which is the x square. The other is the logarithmic function, which is 1 plus ln x. So we integrate the algebra and we differentiate the log. You know this standard by parts method. So what do we get here? Minus 2 into integral of x square is x cube by 3 into 1 plus ln x minus integral of x cube by 3 into derivative of 1 plus ln x, which is same as 1 by x, okay. Now luckily this x gets cancelled here, so x square will remain. What is the integral of x square? X cube by 3. So these terms will give us minus 2 into x cube by 3 into 1 plus ln x minus x cube by 9, and of course there must be a constant c, okay. So now this is equal to x square into z. But what is z? We already know z. Z is 1 by y square. So this is basically x square by y square. Now how do we get y here? Of course first we will divide with x square and then we reciprocate it, or you can leave it like this, or you can write an expression, it does not matter, okay. So if you look at the overall process, so we will get an idea only when we form y dash term and the y term. We need to form these 2 terms always, okay. So that is how we got the idea, and after that it is the standard approach. If you look at the earlier question also, here also it is the same idea. We had to form y and y dash here, but in terms of y we could not form. But when I assumed e power y to be t, I got t dash and t directly, okay. So when we are solving any equation in this chapter, first we try for the variable separable. If it does not work out, then we go for this idea, okay. Come on, make a note of this. This page also. Now let us move to the next question. This question is actually an interesting question because there is integral involved. Now, in general, if you look at the standard form, this is not looking like it is in the standard form, but there is a hint in the question. So, that is what I keep telling every time. If you look closely, there are hints in the given question only. Here, there is an integral where integrand is y. See, there is y involved here, and if you notice, there is y here. So, if I integrate f of x, so for that expression, if I take the derivative, that means derivative of the integral of the f of x, it always gives us f of x, right. So, that means I can somehow express this first term as a derivative of the second term. There is this idea that is coming as the hint from the question. So, what we will do is we will assume this second term to be a new variable z or t. Okay. So, suppose let us say I take this as z because there is already t there which may confuse you. Then, and if I differentiate it and check, that checking process will give us the next step. So, basically we do not get ideas completely, we will get some hints, we are just exploring that hint now. Now, let me take this z and differentiate this. So, what will be the z dash? For this we have to apply Newton-Leibniz theorem of differentiating integrals. So, how do we differentiate here? First put the upper limit, which is y of x by 1 plus x square into derivative of the upper limit, which is 1, minus we put the lower limit, which is y of 0 by 1 plus 0 square into derivative of the lower limit, which is 0. Because lower limit is constant, this term is mostly 0 whenever the lower limit is constant. So, that means we basically got this idea that y is equal to 1 plus x square into z dash. We got this idea. So, that means it can be expressed in the standard form. So, let me just substitute and see if it can be expressed in the standard form or not. So, it becomes 1 plus x square into z dash plus 2x into z is equal to 3x square plus 2x plus 1, right. Now, further we can go for the idea of the integrating factor and integrate it, but that is generally long process. Here I can see directly that derivative of 1 plus x square is nothing but the 2x. So, which means 1 plus x square into z, if I differentiate this product of two functions, I am basically getting this LHS. So, I am using this idea because I just spotted it in the question. So, what is the RHS here? 3x square plus 2x plus 1. Now, that means if I integrate this directly, I can get the resulting value. So, basically you can write this as 1 plus x square into z is equal to integral of 3x square plus 2x plus 1 into dx. So, now you know how to integrate this because this is a polynomial function. So, 3 into here we get x cube by 3, right, 3 into x cube by 3 plus 2 into x square by 2 plus x plus some integrating constant c, and here 2 gets cancelled, 3 also gets cancelled. So, we got an expression for z here, but look at the assumption of z. We have assumed z to be a definite integral. Now, whenever you assume a definite integral to be a new variable, you can find some initial values. These are called as initial values or boundary values. We will discuss these values in the subsequent lectures. Now, initial value or boundary value means, suppose here if I put x equal to 0, what is happening to z? At x equal to 0, z is nothing but 0 to 0 y by 1 plus t square into dt. Now, if limits are equal, the integral is going to be 0, which means at x equal to 0, our output is 0. Using this relation, I can find this integrating constant. So that means at x equal to 0, I should get z equal to 0. This will imply that 1 into z is equal to 0 plus 0 plus 0 plus c. Because z is already 0, c also must be 0. Which means our function z will come out to be x cube plus x square plus x divided by 1 plus x square, right? So we can just write 1 plus x square here. Now solving for z is completed, but we have to solve for y. Now look at what is y. Y is basically 1 plus x square into z dash. So here we have to differentiate this. Now before differentiating, it is better to simplify this into a simple term. So here I can observe that it can be written as, if I take x common, it can be written as x square plus 1 plus x divided by 1 plus x square, right? So we can write this as x into 1 plus x square by 1 plus x square. So again for simplification, we can do plus 1 and minus 1 here in the numerator. That will further give us an expression like x plus 1 minus 1 by 1 plus x square. This is our z. Now what about z dash? We can directly calculate z dash from here. I will just take that to the next page. So z dash is going to be, derivative of x is 1, derivative of 1 is 0, and derivative of 1 by 1 plus x square is minus 1 by 1 plus x square whole square into 2x. Okay. So if I simplify this, I am going to get 1 plus x square whole square plus 2x divided by 1 plus x square whole square, right? Now y will be equal to 1 plus x square into z dash. So that means in the denominator 1 plus x square will get cancelled and 1 will remain. Now numerator we have to simplify. So what is the highest power we will get? X raised to 4. What is the second highest power? X square. So that will be 2x square, and there is one 2x term and there is 1. So this way we can write the function completely. Okay. So here if you notice, what is the main crack step? What is the main killer step? It is assuming that this integral is equal to z. So sometimes when questions are twisted, you can also use ideas like this. Okay. Come on, make a note of this. This page also. Also this page. Okay, so now we will move on to the next question. So for every method, I am also putting some story problems. Story problems means data and information is provided in terms of a story. Using that story, we have to develop one differential equation and then solve that differential equation. So here there are actually two stages of the problem solving. One is developing one differential equation, second stage is solving it. So this first stage of developing the differential equation is called as mathematical modeling. Okay. So this is the general knowledge term for your future. It's called as mathematical modeling. So basically we are going to model the problem in terms of algebra. That is called as mathematical modeling. So how do we do that? We have to represent the entire data in terms of the algebra. So let us read the question first and then we will put the data. So here find the curve such that area of the rectangle constructed on the abscissa, So that means we have to take abscissa as one of the sides, okay. And next, and the initial ordinate of the tangent at this point. Now what is the meaning of the initial ordinate? Initial ordinate or initial abscissa, this means x-intercept and y-intercept. Remember that for any line, on any line there are actually infinite points, right. So for every point there is one abscissa, there is one ordinate. So like this, if you look for the entire line, there are infinite abscissa and infinite ordinates. But when we say initial ordinate, it means y-intercept. When we say initial abscissa, it means x-intercept, okay. So that means, let us say if this is my tangent and let us say this is my curve, I take this curve as y equal to f of x and the point as let us say h comma k. Now there is x axis here, there is let us say y axis here. What is the abscissa of this point? Abscissa is basically the x coordinate, which means from here if I draw one perpendicular, this distance is going to be the abscissa, which is h comma k, okay. So see, this I keep on saying, whenever you are solving story problems, take the point as h comma k initially, and at the end after you get the differential equation, you may go for the x and y variables, okay. So this is our abscissa of the point. So this has to be one side, okay. So this has to be one side, and the next, the initial ordinate of the tangent. So what is the initial ordinate? This height is the initial ordinate, which is same as the y-intercept. So what is the rectangle that is formed here? The rectangle formed is this. Rectangle formed is this rectangle, which I am drawing in terms of the red shaded region, okay. Now here it is given that the area of this rectangle is equal to a square. So how do we do this problem? We have to start with the tangent, find the y-intercept. We already know the base, so base into height is going to give us the area, okay. So how do we do that? We first write the equation of tangent, which is y minus k by x minus h is equal to k dash, that is the slope of the tangent. Now in this, if we put h equal to 0, what do we get for x equal to 0, what do we get for y? For y we get k minus h k dash. So that means the height is going to be k minus h k dash. What about the area now? Area will be h into k minus h k dash. This will be the area, is equal to a square, right? Because area is given as a square. With this we can solve the problem. No, not so fast, because you don't know whether these coordinates are positive or negative. See, that's what we call as completeness of solving a problem. So we don't know if LHS is positive or negative, but we know for sure that RHS is non-negative because there is square there. So we have to put mod here, okay. We have to put mod there. So because of the modulus, we may get two cases, okay. So one with the plus, one with the minus. So I'll solve with one sign, you can solve with the other sign, okay. Now let us convert this into the standard form and solve it. So what do we get? So I am taking only the plus sign, case 1, where mod is taken as plus sign. So that means we will get x into y minus xy dash is equal to a square. So now convert this into standard form and solve it. So what is the best way to solve this? We have to make sure that coefficient of y dash is always plus 1. So we have to divide with minus x square. So that will give us minus 1 by x into y and plus y dash is equal to minus a square by x square. So now it is the standard process, find the integrating constant and then simplify it. Okay, so let's go for the integrating factor. So it is y dash minus 1 by x into y is equal to minus a square by x square. What is the integrating factor? It is e raised to integral of minus 1 by x dx, which is going to give us e raised to minus ln x, which is same as e raised to ln of 1 by x, which is also same as 1 by x, right? So further how do we do it? Integrating factor into dependent variable is equal to integral of integrating factor into RHS dx. So here we are basically getting minus a square into integral of 1 by x cube dx. So how do we integrate it? It is one of the standard forms. So we will get x raised to minus 3 plus 1 divided by minus 3 plus 1 plus some constant c. Now when we simplify this, what are we going to get? We will be getting, here it is anyways minus 2, so minus minus will get cancelled, we will get a square by 2 and into 1 by x square, there is plus c here and here it is y by x. So y will be equal to a square by 2x plus cx. Okay. So this way we can solve the problem. But hold on, we have taken only one sign here, right? Plus sign. What if I had taken the minus sign? If I had taken the minus sign, the only term that will change will be this a square term. So in place of a square we will be getting minus a square. So that means every term will be same, but only thing is this, for this term we have to reverse the sign. So if we keep on doing it, what is the term that will change in the solution? Only this term will change in the solution. So we can write the final answer as, y equal to cx plus minus a square by 2x. Now the reason why I have put plus minus is, of course I have explained here, only this term will carry the opposite sign, only a square term will carry the opposite sign, so hence we have taken the other sign also. So here you don't have to worry about both cases at the same time. If you solve one case and if you logically deduce an information like this, then also it would be fine, right? So this way we can solve the problem. But hold on, sometimes this question could also mean something else, but that may change depending on the situation. So here we have taken abscissa as the x coordinate, which is distance travelled along x axis. If you take the abscissa as the perpendicular drawn to y axis, then your rectangle may change. Okay? For example, if this is the curve and if this is the random point and we have the tangent here, so it is intersecting at some point. From this point, if you take only perpendicular drawn to y axis as the base and if you take this length as the height, so you may get a rectangle like this, and this rectangle may have different area than the earlier setup. So which means here the question will be completely different and the answer also will be definitely different. So which also implies that this question may mean two different approaches, okay, and that means that leads to two different answers. It is always possible. So that is why first do the most obvious case and then also explore the other case. If this was a multiple answer question, then of course both these answers should be treated as correct, okay. So this way we can solve the problem. Come on, make a note of this. Next page also. Okay. So now let's go to the next question. Next question is, find the curve such that y-intercept cut off by the tangent on any arbitrary point is proportional to the cube of the ordinate of the point of tangency. So here also we have to follow the same setup. So it is the same approach, we have to draw a curve, we have to take x and y axis, and for the tangent we have to take the y-intercept, which is same. So when you take the point as h comma k, when you take the curve as y equal to f of x, it is going to be the same setup. So let me take the y-intercept from the earlier case. So this is our y-intercept, okay. So what is given here? It is given that y-intercept, which is k minus h k dash, this must be proportional to the cube of the ordinate. What is the ordinate of the point? It is k. So cube of the ordinate must be k cube. Now if we get rid of the proportionality, we have to introduce one proportionality constant. Let's take it as c. Okay. So now it is in the standard form of any standard differential equation. So we'll put h equal to x, k equal to y, and then convert this into the standard form and then see what kind of form it is. But of course we can make out that this is one of the forms that we have discussed. Okay. So if you observe the LHS, LHS is basically linear form, but RHS is actually causing trouble. So we may have to divide with y cube. Okay. So before that, let me just write this in standard form. So y dash minus 1 by x into y is equal to minus c by x into y cube. Okay. So now this is in the convertible to linear differential equation form. So we have to divide with y cube. When we divide with y cube, what happens? We get y dash by y cube is equal to minus 1 by x into 1 by y square is equal to minus c by x. So you know our approach, we take 1 by y square as the z, which is our new variable. Now we have just done it in the earlier question. So where we have taken 1 by y square as our z, right here. So if 1 by y square is z, y dash by y cube is minus z dash by 2. So let me just use these results just to save time. Okay. So this is minus z dash by 2 minus 1 by x into z is equal to minus c by x, and what is our z? Z is basically 1 by y square. So now let's simplify this and convert this into the standard idea. So it becomes z dash. I am basically multiplying with minus 2 and it becomes 2 by x into z, right. Now we managed two terms. Now the RHS, it will become 2c by x. Now integrate this, this will be in the standard form. So integrating factor is e raised to integral of 2 by x dx. So we've been doing this, it becomes e power ln x square, which is also same as x square. So integrating factor into dependent variable is equal to integrating factor into RHS dx. Okay, it is 2c by x. So now what happens? This will give us, if I take 2c common, it will give us x dx. So which is same as 2c into x square by 2 plus constant, let's say k, and 2 got cancelled. Okay, so we already used k in the problem solving process. Let's take it as d. Okay. Now further, we know that z is basically 1 by y square. So it is going to be cx square plus d. We can write the function as 1 by y square equal to c by x square, c plus d by x square. Or we can leave it. So this way we can solve the problem here. Okay. So every time whenever we get a story problem, first we need to develop the mathematical model and then we have to solve that model. Okay. So, this way we can solve the problems. Okay. So, with this we close the linear differential equations part and we will go on to the next part. Okay. Come on, make a note of this. Okay. This page also. Okay. So, now let us go to the next concept. This is called as homogeneous differential equations. Now, we know the term differential equation, but we do not know what is homogeneous differential equation. Before that, let us understand the homogeneous part first. What exactly is the meaning of the homogeneous? So, in general, whenever we see this homogeneous, we might have seen this in chemistry also or maybe in physics. What is the meaning of homogeneous mixture? It means the particles should be uniformly placed all around the solution. So, similarly, if we apply that to mathematics, in mathematics what is it that we are dealing with? We are dealing with equations most of the time. Mathematics means equations. So, homogeneous means that equation or expression must be uniform. So, in terms of what it must be uniform? In terms of the degree of each term. So, if each term is having uniform degree, which means same degree for all the terms, then that equation is called as homogeneous equation. If it is an expression, we call it homogeneous expression, right. So, that is the simple logical term. Do not go to the definition first. So, let me first explain you this idea and then we will go to the definition. For example, let us say I take this equation ax plus by plus cz plus some constant phi equal to 0. Is this a homogeneous equation? Of course not, because this has degree 1, this has degree 1, this has degree 1, but this has degree 0. So, degree is not uniform, so it is not homogeneous. To make this homogeneous equation, we have to make sure that constant term is not present, right. So, it becomes homogeneous equation. Now, suppose let us say I take an expression x square plus 2xy. Is this a homogeneous expression? If you check the degree of the first term, it is 2, degree of the second term is also 2, because x has degree 1, y also has degree 1. So, effective degree of the second term is 2. So, hence this expression is also homogeneous expression. Okay. So, now you have understood what is the uniformity, but every time for every expression we cannot keep on checking every term. So, there is a standard algebraic definition for homogeneous expression. What is the definition? Suppose let us say I have taken an expression in terms of only 2 variables. Of course, we can take any expression in terms of any number of variables, but here I am explaining it only for the 2 variables because our chapter is also having only 2 variables. One is independent, one is the dependent. So, let us say there is an expression f of x comma y. We will call it homogeneous expression if it satisfies the condition. What is the condition? In place of x, if we put lambda x, in place of y, if we put lambda y, and simplify that expression, all the lambdas that we have introduced must be uniformly taken common. If that is happening, we call it as homogeneous expression. Okay. And whatever is the degree of lambda that we get outside, it becomes the degree of the homogeneity. For example, let us say I take this expression, I take this as f of x comma y, then f of lambda x comma lambda y, we can write this as, see, in place of x I am putting lambda x, so lambda x here whole square plus lambda y whole square. So, this is going to, this is lambda y into lambda x into 2, right, it is 2xy term. So, 2 into lambda x into lambda y. Now, if you notice, we can take all lambdas common. So, we can write this as lambda square into x square plus 2xy. So, we could take all lambdas common, and whatever is the expression remained, it becomes the original expression. So, that means this is equal to lambda square into f of x comma y. So, is it satisfying the definition? Of course, yes. So, hence this is homogeneous expression. Now, what is the degree of homogeneity of this expression? Degree of homogeneity is 2. Okay. Now, let us look at this first example that I have given you. What is the degree of homogeneity here? It is 1. After we deleted the constant, degree of homogeneity is 1 there. Okay. So, this way we can understand the basic meaning of homogeneous expression. Okay. Come on, make a note of this. Okay. Now, let us look at some examples of these homogeneous expressions. Suppose let us say I have taken an expression like this. See, every time we may not get one single numerator term or something, we may get denominator also. And here also function or sorry expression may become homogeneous. For example, here if I introduce lambda x and lambda y in place of x and y, then what happens here? So, here we can get lambda x whole square, here it is lambda x into lambda y, plus here it is lambda y whole square divided by lambda y whole square minus lambda x whole square, right. So, see if you can get any lambdas common. From first term I can take lambda square common, from second also 2 lambdas are there, in third also there are 2 lambdas. So, lambda square is taken common. So, what do we get in the numerator? We get x square plus xy plus y square divided by, what about the denominator? Here there is lambda square, here also there is lambda square. So, when I take lambda square common, we get y square minus x square, right. So, here if you observe, both lambda square got cancelled luckily, and whatever remained is the original expression. So, we can write this as lambda raised to 0 into f of x comma y. So, is it in the standard form? Yes, of course, this is the standard form. So, it is homogeneous expression. What is the degree of homogeneity? It is 0. Degree of homogeneity here is 0. Okay. So, this is one idea that we explored here. Also, there is something that you can notice here. If you look at the only numerator, it is homogeneous expression of degree 2, and if you look at only denominator, that is also homogeneous expression of degree 2. So, when we divide it first with the other, the net result is also homogeneous expression and degree got cancelled. Now, there are two aspects here. One aspect is, when numerator has certain degree of homogeneity, denominator has certain degree of homogeneity, when we divide one with the other, the net degree is going to be the m minus n idea. You know that exponents idea, a power m by a power n equal to a power m minus 1. So, degree of homogeneity is power of the numerator minus power of the denominator. This is one aspect. Second aspect is, let us say you have taken two homogeneous expressions, okay, two homogeneous expressions. If you add these two, the result will be homogeneous only if these two are having the same degree. But even if these two do not have the same degree, the product or the ratio of these two will always be homogeneous. These are some tips for your general knowledge. Okay. Now, let us look at another example of the homogeneous expression. So, here if you notice, tell me if this is homogeneous expression or not. This is of course not a homogeneous expression. Why? Because if you notice, this is having degree 3, this is having degree 3, and this is not having degree 3, that is having degree 2, So, uniform degree is not maintained, so it is not homogeneous. So, this way sometimes by looking at this we can say, okay. But even if numerator has completely uniform degree and denominator has completely uniform degree, there is also this need for the checking of the degree of homogeneity. That is why you need to understand the effective degree of the numerator versus denominator, okay. So, of course, this is not homogeneous expression. So, we have understood what is homogeneous expression, what is not, right. Now, let us look at the homogeneous differential equation. So, in general, homogeneous differential equation looks like this: y dash is equal to some expression. Now, this expression will be having both variables x and y. If the RHS expression, the expression in the RHS, if this is homogeneous expression, then the equation is called as homogeneous differential equation. Not so fast, just wait. But there is a condition. Condition is degree of homogeneity of the RHS must be 0. Why? Because if you look at the LHS, LHS is basically dy by dx. What is the effective degree of the LHS? It is 0, because numerator has degree 1, denominator has degree 1. So, effectively the degree is 0. So, that means this is like net 0 degree. So, RHS also must be having net 0 degree, okay. So, this way we can define the homogeneous differential equation. So, if you now you can read the definition. So, it says this is called as a homogeneous differential equation if f of y comma x or f of x comma y, it does not matter, because we are just representing expression here, is homogeneous expression with degree of homogeneity 0, okay. So, this is the main definition of the homogeneous differential equations. We have understood what is homogeneous expression equation, what is homogeneous differential equation. Now, let us look at how to solve this. So, to solve this there is a very standard method. What is the standard method? Okay, so before you understand the standard method, there is one important idea that we have to discuss. Suppose let us say I have taken one example f of x comma y is equal to x plus y by x minus y. Tell me if this is homogeneous expression or not. Of course, it is homogeneous. We can see that in the numerator all terms are uniform, denominator also all terms are uniform degree. So, it is homogeneous expression. Now, what is the degree of homogeneity? Numerator has a degree of homogeneity 1, denominator has a degree of homogeneity 1. So, effective degree of homogeneity is 0, okay. Now, whenever there is an expression with effective degree of homogeneity as 0, we can always write that expression as a function of y by x. That means, by taking an appropriate power of x and dividing this, both sides numerator and denominator, we can convert this into a function of y by x. For example, here if I divide with x, what do I get? 1 plus y by x divided by 1 minus y by x, right. So, I can write this as a function of y by x like this, 1 plus y by x divided by 1 minus y by x. So, this y by x becomes our variable. So, here you can understand that any expression, any homogeneous expression of the degree of homogeneity 0 can be expressed as this idea, okay. So, we can also look at the earlier example. For example, this here if I divide with x square both sides, what do we get? F of x comma y is equal to 1. So, xy by x square will be y by x, y square by y square will be y by x whole square divided by y by x whole square minus 1, okay. So, this way any homogeneous expression of degree of homogeneity 0 can be written as a function of y by x. that will give us the basic idea of the method. So that means we can write the RHS as a function of y by x, right. So if RHS is written as a function of y by x, what is our immediate thought? Take y by x is equal to one new variable. We can take it as t, and then using this substitution, when we simplify the expression, it is going to get converted into the variable separable method. That is the beauty of the homogeneous differential equation. Okay. So I think due to time constraint, we will stop at this point. So meanwhile, you go through this theory and try to prove this, try to understand what is happening here. In the next lecture, we will start with the same page, we will discuss it, we will see some example, we will learn the method, and then we will move on to the next ideas. Okay. So we will meet again in the next lecture with more concepts. Until then, have a great learning day, learning shall never stop.